In this video, we're going to look at calorimetry, which is really just a way of measuring the amount of heat that's absorbed or released by a reaction after it causes a temperature change in the surroundings. So any quantity of heat can cause a temperature change to happen in a substance. The heat capacity is the amount of energy required to raise the temperature of a substance by 1 degree, whether it's Kelvin or Celsius. That's the same value, it's just that they have different starting places. Absolute zero in Kelvin is negative 273 Celsius. But different substances have different heat capacities. And you might even notice this, like if you were to microwave some of your food in the microwave and you have a whole assortment of different foods, some things heat up faster than others. Like one of your vegetables might be really hot, but your meat is still really cold because they have different heat capacities. The greater the heat capacity, the greater the amount of heat that's needed to produce a temperature change. For pure substances, heat capacity is given for a specific amount of substance. So there's two different heat capacities that you might see. One might be the molar heat capacity, and that's the amount of energy required to raise the temperature of 1 mole by 1 degree Celsius or Kelvin. Or you might see it on a per mass basis, which we then call the specific heat capacity, or sometimes just specific heat for short. And that would be the amount of energy required to raise the temperature of 1 gram of a substance by 1 degree. Notice that their units would then be different. So molar heat capacity would be joules, the energy needed, per mole degree Celsius, or per mole degree Kelvin. Mole and Kelvin, or mole and Celsius, are on the denominator. And specific heat would have similar units, but grams would be replacing moles. So how can you calculate heat if you have a temperature change? We can use this equation, Q equals mc delta T. And some people remember it as Q equals mcat because it looks like an mcat. But this delta is representative of change. This is on your formula sheet for AP Chemistry, and it does define what these different variables are, but it doesn't remind you about units. So it is really helpful to keep units in mind. Notice Q is heat, M is mass typically in grams, C is specific heat capacity. We just talked about usual units for those, energy over, if it's specific, that's per gram basis, and Celsius or Kelvin in the denominator, and T, temperature change. There are no specific heat values that you actually need to memorize for the AP exam, but in some problems it might be helpful to know that water's heat capacity is 4.18, units being joules per gram degree Celsius. On an exam or any AP exam, any values that you need for this would be given, or you could be solving for it. So you always just read the problem to get that information. Remember that each substance will have a different heat capacity. Sometimes on an AP exam, rather than this being the heat capacity of water, they might even give the same value as the heat capacity or specific heat of the entire solution. So just always read the problem to get this value. So a couple takeaways from this equation here is that a given amount of heat will not produce the same temperature change in equal masses of matter if they have different specific heat capacities. So if you have two substances that are different, and they are made of two different substances, they will have two different heat capacities. So even if you're applying the same amount of heat, the same Q, and you have the same mass of each, whichever substance has a higher heat capacity for all these two things being the same, your change in temperature is going to be lower. So something that has a higher heat capacity for the same amount of heat for the same mass, the temperature is not going to change as much. So the higher the heat capacity, the smaller the change in temperature. Notice that these are inversely proportional. So you should be able to glean some information about relationships from any time you have an equation. Okay, take a moment and try this example. Here is a chart, and here's specific heat capacities. These are per kilogram rather than gram, but it's still heat per mass unit per temperature. Take a moment and answer these two questions and then check your work. So these are all different metals. and I want to know which will experience the largest change in temperature for the same amount of heat and the same amount of mass. So if I think about my equation, okay, I'm looking for something that has a lower heat capacity. A lower heat capacity means it would take less heat to change the temperature, so the temperature is going to change more greatly. So silver here has the lowest heat capacity, so it's going to change temperature the most. Which will change temperature the least would then therefore be aluminum. It has a really high heat capacity in relation to the others, so it's going to take more heat to cause the same temperature change. So again, make sure you can think about this relationship. I see this on the AP a lot, the relationship between heat capacity and the change in temperature. So just because two substances absorb the same amount of heat does not mean they're going to have the same temperature change. So here's an example, just plug and chug kind of into QMC delta T. Give it a shot just to practice and be aware of units as you plug in. So check your work. Here's QMC delta T. They give me a mass of water in grams. They don't give me the heat capacity, but this is where I said, hey, it's helpful to remember the heat capacity of water. If this was on an AP exam, I would give you, or any type of exam, I would give you the heat capacity, 4.18. But you're going to be using it a lot. It might even just come into your memory by kind of naturally. And then delta T is the change in temperature. Now notice when I plug in my units, okay, MC delta T, the grams cancel, so it would be important to have my mass in grams. If it was like kilograms they gave me, I'd have to convert. And the Celsius cancels, and I'll be left with joules. Now the question asked me for the heat in kilojoules, so that's where I say be careful of your units, because if you're on a free response question, you might forget to do the last step of converting to kilojoules. There's 1,000 joules in 1 kilojoule, so you're really just dividing by 1,000 or moving your decimal place over one place, and you get 3.135. I should probably simplify this to less sig figs. Since this actually only has 1 sig fig, I should really just write 3 kilojoules. Okay, so again, my note is be aware of units. In this chapter and in a lot of chapters, you can go wrong really easily if you don't plug in units and see what cancels. So again, if your C is in, use your C kind of as your guidance. So if your C is in a per gram basis, I need my mass in grams, I need my delta T in Celsius to cancel, and I would end up getting joules for heat. So usually when you plug into QMC delta T, you end up getting joules. But again, check your C units, and that's going to really give you guidance. So now we know how to calculate heat with this equation if I have a temperature change. So how can I use this information to calculate the delta H that I see in the thermochemical equations like we were looking at in the last video? You can write an equation, you see a delta H value. How can I use this equation to calculate delta H, which if you remember we said is really kilojoules per mole. And here, Q that we're calculating is typically just joules. So in an experiment, you would use what's called a calorimeter. So a calorimeter is something that it's using constant pressure, so your heat is going to be related to delta H. And it's basically something where you're carrying out a reaction in an insulated container, insulated so that we don't lose any energy to other surroundings. And you're typically carrying out the reaction in water, in some type of solution that you can know the heat capacity of. That's why I say usually water, because we know the heat capacity. Sometimes I've even seen problems where they're like carrying it out in sand and they give you the heat capacity of sand. But basically you are carrying out a reaction and it's going to cause some type of temperature change in the surroundings. In this case, the surroundings would be water. Okay, so there's a couple of steps that you would want to do in an experiment. So first you would measure out the mass of the water to put in your cup, and you would add it to your insulated container, and you would measure the initial temperature. So then what you would do is you would measure out the mass of the reactants that you want to react. Okay, then you would put those reactants into the water, and you would carry out your reaction. And based on the reaction, the temperature change of the water is going to tell you if it's endothermic or exothermic. So remember, if the temperature goes up, of the surroundings water. The water is functioning as the surroundings. So if the water temperature goes up, that means heat must be released into the water. So the reaction is exothermic. It's causing a temperature change to go up. If the temperature is going down of the water as the reaction goes, that must mean that the reaction's absorbing heat from the water. So that must mean the reaction's endothermic. So once the reaction's carried out, you record the final temperature of your water. Essentially, you're recording the lowest temperature you reach if temperature's going down, or the highest temperature you reach if temperature's going up. So basically, now you have your data to plug into mcΔT. You can find out how much heat was absorbed by the water or released by the water, which is your surroundings. So you had your mass of water that was in your container, you had your initial temperature and your final temperature, your delta T, and you can look up the heat capacity. So notice all of these variables, mcΔT, they're all about the same thing. They're about the surroundings. In this case, the surroundings is water. If you carried it out in something other than water, like sand, it would be the mass of the sand and the heat capacity of the sand and the change in temperature of the sand, or whatever. Now, whatever the water's doing, just remember that the reaction's doing the opposite. It's like I was saying, if the temperature of the water's going up, that means that the reaction is actually releasing energy, and the heat would have a negative sign. It would be exothermic. And then you've successfully gotten the heat that's absorbed or released by the reaction. Awesome. Now, just remember that the reason we're carrying this out in an insulated container is that we want all the heat that was absorbed or released by the reaction to go into the surroundings, in this case, just the water. We don't want it to go beyond this calorimeter, so that's why it's insulated, so that the heat lost by the reaction is gained by the water, and vice versa. That's why we have this. Usually it's a styrofoam cup. It could be some other type of insulated container. We don't want to lose heat beyond our surroundings being water. Okay, so typical calculations, you would just find the heat absorbed or released by the water. Okay, again, mcΔT, but with water. Then we would just say this is the exact same magnitude that's lost or gained by the reaction, but it would have opposite sign because it's in opposite direction. If the water gained energy, that means the reaction lost energy, and vice versa. So it would have the same magnitude, but a different sign. And then if you remember, Q has units of joules. So a lot of times if we're going to be asked for the molar heat of the reaction, the delta H, and that has units of kilojoules per mole. If we're in this step here, we're just in joules. So what we would want to do is we would want to take the joule amount that we got here, the heat in joules, obviously convert it to kilojoules, but then notice it's on a per mole basis. So I need to divide by the moles of the reactant that I had to start with. If I have just one reactant, like a lot of dissolution reactions where you're just dissolving something, then you just take the gram amount that you measured out of your reactant. We said we were measuring out, if you remember in this step, I said measure out the mass of the reactant. Okay, you're using that mass to turn it into moles. And then you're just taking your joules, changing it to kilojoules, and dividing by the moles you start with. Like I said, the only thing is if you have more than one reactant and you have the masses of each reactant, it becomes a limiting reactant problem. So you basically just have to make sure that you're dividing by the moles of the limiting reactant, because that's what's going to limit the heat that was produced as well. So you're just dividing the Q of the reaction in kilojoules by the moles of the limiting reactant. Okay, so this is a nice little step-by-step to have all in one place, but let's do a problem so you can see how this is applied, because it might seem more complicated in me explaining this than actually doing the problem. Okay, so again, another little problem-solving technique. Get the magnitude of the heat lost or gained by mcΔT, okay, and then just get the sign by examining the temperature change in the problem statement. So if the temperature of the surrounding water increases, the reaction's exothermic. And then the delta H or the Q for the reaction should have a negative sign. If the temperature of the surrounding water decreases, okay, that means the heat was released into it, That means the heat was absorbed by it. The reaction absorbed heat from it. Then the reaction's endothermic, and the Q or delta H should be positive. So I'm getting the sign just from the analysis of the problem. If you want to omit positive and negative when you're doing math, just get the magnitude from QMC delta T. Get the sign from seeing what's happening to the temperature change of the water. So like I said, let's do an actual problem. Take a moment, try it yourself, and then pause the video, then check your work with the video. So a coffee cup calorimeter contains 120 grams of water at 20 degrees. Reactions carried out and the final temperature of the water is 35.6. Here's the specific heat capacity of the water, and I want to know two things. How much heat is absorbed or released by the water, so they denoted that QH2O, and how much heat is absorbed or released by the reaction, so they denoted that QRXN for reaction. So I can figure out what's happening to the water. The water is going through a temperature change, so I can use QMC delta T. And I just put subscripts of H2O to remind myself this all has to do with H2O. So I'm using all H2O values here. So the mass of water, the specific heat of water, and the change in temperature of the water. So the mass of the water is 120. Specific heat is 4.18. Okay, put in your units, you can see what cancels, and my temperature change going from 35.6, it started at 20, so I subtract those two values. And I get 7,820, and my units should be joules because grams cancel and Celsius cancel. They don't specify what unit I need here. If I wanted to, I could change to kilojoules by dividing by 1,000 or not. It's up to you because they don't indicate the unit. But I should have a unit with my number. Now this is the heat that is absorbed by H2O. Why is it positive? Because the temperature is going up. The water has absorbed energy. Now, if the water is absorbing energy, what's happening to the reaction? The reaction's releasing energy, so the reaction is exothermic. So it's the same magnitude, but opposite sign for part B. If this is about 8,000 joules that are positive, this should be about 8,000 joules, but negative. Okay, just a note to read the question. Okay, sometimes coffee cup calorimeter problems give you the specific heat of water. Then you use everything about the water, mass of water, heat capacity of the water, change in temperature of the water. The water is the surroundings. Sometimes an AP problem might give you the specific heat of the entire solution. They might say the specific heat of the solution is 4.18, whatever. If they give you the heat capacity of the entire solution, make sure you're using the mass of the entire solution and not just water. So that might mean adding up the reactants and the water because that would be the mass of the whole solution. So whatever your heat capacity is given of, that's what you want to use the mass of. And the same thing goes like if it was something different, like the reaction took place in sand, then you would use the mass of the sand. If it took place in some other solvent, you would use the mass of that solvent. So you're really just using heat capacity. You look in the problem, what did they give you the heat capacity of? That's what you should be using the mass of in QMC delta T. Okay, take a moment, look at this problem, and give it a shot. A coffee cup calorimeter contains 80 grams of water. 6.7 gram sample is dissolved, so it's a dissolution reaction. It's something dissolving, and the temperature changes. It goes up to 60 degrees. I give you the specific heat of the solution. Okay, that's good to know. What is it of? It's of the solution. That means the entire contents of the calorimeter. Calculate the heat of dissolution. So QMC delta T, everything is going to be based on what my specific heat is. My specific heat is of the solution, so I want to make sure I'm using the mass of the solution. All these variables should be of the same thing. So the mass, they give me 80 grams of water, but they don't give me the heat capacity of water. They give me the heat capacity of the whole thing. So I need to add 80 plus 6.7 in this problem. So really be aware of what they give you the heat capacity of, because I've seen this like this on the AP, and you need to add if they give you the entire solution. If they just give you water, then you just use the water. Okay, and then here's my specific heat. Here's my temperature change. Pay attention to units, and I'll notice that I get joules as my answer. So this is how much heat is released essentially into the solution, since the temperature of the solution is going up. So the reaction which is a dissolution reaction, calculate the heat of dissolution, would be the same value but negative, and they didn't specify units, but I changed to kilojoules just since it's a pretty large number by dividing by 1,000. Okay, so again, it should be negative, make sure, because heat was released, temperature went up. I'm using the information in the problem statement to figure out my sign. Just a terminology note in case you were confused, heat of dissolution, what does that mean? When a substance is dissolved, the terms heat of solution or enthalpy of dissolution may be used rather than heat of reaction, because the reaction is a dissolution reaction. Something is dissolving. Dissolution is the noun of dissolving. You might be asked for molar heat of solution or molar heat of dissolution in kilojoules per mole. And that would be calculating delta H, because that's on a per mole basis. That's why they say molar. Okay. So when a substance reacts, rather than saying heat of reaction, a question may refer to the exact reaction instead, like heat of combustion if it's a combustion, heat of neutralization if it's a neutralization, acid and base, heat or enthalpy of decomposition if it's a decomposition. So don't get thrown off by that terminology. And if you see the word molar in front, that's implying delta H. That's implying it's on a per mole basis. Okay, so let's kind of expand upon that problem. We talked about delta H. Now let's look at that. So let's say part B, the same problem. Part B is the sample that was completely dissolved was LiBr solid. Calculate the molar heat of solution in kilojoules per mole. So they want the delta H in kilojoules per mole. Once you find that, write a thermochemical equation. Take a moment and try the problem, and then we'll go over it together. Okay, so we knew from the last part, from part A, that when all the 6.7 grams dissolved, okay, the heat goes into the water, into the solution, and that we calculated that the actual heat that's released by the reaction is 12.7 kilojoules. It's exothermic, so it's negative. Okay, but this is how many kilojoules are released when 6.7 grams react. I need it on a per mole basis. I need it not when 6.7 grams react, but when 1 mole of it reacts. So it's really just a little bit of a conversion here of changing the grams, the starting grams of LiBr, to moles using the molar mass. Now what's nice about a dissolution is that there's only one reactant. So I only have to change the 6.7 grams to moles, and then I can divide my negative 12.7 by 0.007 moles of the LiBr, and now I have my units in kilojoules per mole. So all I'm doing is making sure my energy is in kilojoules and dividing by the moles of reactant I started with. Really simple. The only time that this can get a little more complicated is if it were not a dissolution, I had 2 reactants, and I gave you the amounts of both reactants. Then you would have to first figure out what's limiting and make sure you're dividing by the moles of the limiting reactant. Okay, and then it asks, write a thermochemical equation. So this is my delta H. So all I have to do is show the dissolution of LiBr solid. So I would be starting with LiBr as a solid, and it would be dissolving into and breaking up into its constituent ions, Li plus and Br minus. It's a strong electrolyte, group 1, it's fully soluble, so it completely breaks up. And my delta H would be negative 164 kilojoules. Another way of writing this thermochemical equation, if you want, is this 164 kilojoules would be the heat released when 1 mole of this breaks up. So I could rewrite this, and rather than putting delta H as negative 164 kilojoules, I can put plus 164 kilojoules as a product, because Li plus is formed, Br minus is formed, and 164 kilojoules are also formed or released as a product in this reaction. Had delta H been positive, if it were, let's say, positive 164, then I could put plus 164 on this side instead, on the left side, because 164 kilojoules would be needed. And that's why you can use delta H as a conversion factor, because it is really just like one more thing in your reaction. You can convert between kilojoules of heat and moles of any of these components using the coefficients. We'll look at a few more examples of this in class.